Dear students, Assalamu alaikum. In our previous videos, we were studying about IR spectroscopy. Today, we will discuss Raman spectroscopy. Raman spectroscopy is also used to detect different functional groups, but in this case, we can observe the vibrational excitation of the IR inactive vibrational modes. So let's start with the Raman spectroscopy. It is based on scattering of light from molecules. So Raman spectroscopy is based on scattering of the light, not absorption of the light. So it can be used for the detection of IR inactive vibrations in which the dipole moment doesn't change. Raman, the scientist, which was Indian scientist Raman, splitted scattered light from sample into three different regions by passing this scattered light through the prism. The scattered light, when passed through the prism, he observed that the light is resolved into three different regions. The region which is scattered and the major region is the Rayleigh line, and he also observed the two other regions which he called Stokes line and anti-Stokes line. The name given for Stokes line is due to the shifting of the scattered light towards longer wavelength, and anti-Stokes due to the shifting of the frequency towards shifting of the wavelength towards shorter wavelength. Now we discuss each one by one. First is the Rayleigh line. It is scattered light without any absorption or interaction with the molecule. So it has same frequency as the frequency of the incident light. The second line is the Stokes line. Stokes line is the scattered light after causing vibrational excitation of the molecules. So it has slightly lower frequency than the incident frequency. The third one is the anti-Stokes line. Anti-Stokes line is the scattered light after the addition of light from vibrational relaxation into the incoming or incident light. So it has higher frequency and shorter wavelength. What is Raman shift? It is the difference between between frequency of the two scattered lines, that is the difference between Rayleigh line and the Stokes line, which gives us the absorption frequency for vibrational excitation. It tells us that how much frequency is absorbed during vibrational excitation. So it is the detection of functional groups by scattered light. If we look at the schematic representation of the Raman spectroscopy, in Raman spectroscopy, the light is passed through the sample. The light source may be the mercury arc lamp. After passing through the sample, the light either it will be transmitted after absorption or the some part may be scattered. So this scattered light is passed through the prism, and Raman observed that this line is resolved into three different regions, out of which the main region was the Rayleigh line, and he also observed two other regions with longer and shorter wavelength. If we look at the absorption frequency, like here we take an example that Rayleigh line or incident light is the 22,950 per centimeter, and the Stokes line is slightly with longer wavelength, which is 22,500. So it is wave number actually. So it tells us the frequency. So the frequency is lowered down, and here is the 23,400, which is higher frequency. If we look at the difference between the two frequency levels, Here is the 450 per centimeter, which is wave number. And if we look this difference in the frequency of the Rayleigh line and Stokes line gives us Raman shift, which gives us the absorption frequency. The same difference will observed between Rayleigh line and anti-Stokes line, because it is the absorption of this 450 per centimeter to this incident light, and now it becomes with higher frequency, so it is in shorter wavelength. If we look at the energy level diagram of the Raman spectroscopy, or how the vibrational excitation or relaxation occurs in the energy levels, so here we can observe that the electromagnetic radiations when fall on a molecule, or we can say the incident light, in case of Rayleigh line, this light is scattered from the lower or ground state of the electronic ground state and vibrational ground state of the molecule. So this represents the Rayleigh line, which is equal in the frequency as it is incident light. In case of the Stokes line, the incident light causes some vibrational excitation, which is from this vibrational energy level, ground vibrational energy level, which is V0. So it goes from V0 to V3. So it goes to vibrational excitation from V0 to V3. Although it is the ground state, but the vibrational energy level is changed. So this vibrational excitation, the energy of this light is absorbed, and after absorption of this frequency, the light when scattered, it is called Stokes line. And sometime when the vibrational relaxation occurs, this vibrational relaxation also produces the light which is added in the incident light, and both of these lights becomes at higher frequency. So it gives the anti-Stokes line. So in this case, we observe three different regions of our scattered light. So in this way, the IR inactive molecules can be detected, and we can observe different functional groups by Raman spectroscopy. So today it's Raman spectroscopy. In our next lectures, we will study NMR spectroscopy. Thanks for watching my videos.